Good afternoon. Welcome back to the webinar series of IEEE MTT APEMC chapter, Islamabad at Research Institute for Microwave and Millimeter Wave Studies at NUST Ashwell campus. I am Dr. Noshawan Shoaib, the chair of the chapter. I welcome you all at this talk. The topic of today's talk is human exposure to RF field. Our guest speaker today is Dr. Masood Rahman from University of Glasgow, UK. Before starting the webinar, I will discuss a brief biography of the speaker. Dr. Masood Rahman received the MSc and PhD degrees in electronic engineering from Queen's Mary University of London, UK in 2006 and 2010 respectively. After his postdoctoral stay, he joined the Center for Wireless Research, University of Bedfordshire as a lecturer. He served briefly with the University of Essex and then moved to James Watt School of Engineering at University of Glasgow, UK as an assistant professor. He has contributed to a patent and has authored and co-authored 4 books, 7 book chapters, and more than 100 technical articles in leading journals and peer-reviewed conference papers. His research interests include compact antenna design, radio wave propagation, and channel characterization. Satellite navigation system antennas in cluttered environment, electromagnetic wave interaction with the human body, body-centric wireless network and sensor, remote healthcare technology, millimeter wave and nano communication for body-centric networks, and D2D and H2H communication. He is a fellow of the Higher Education Academy UK and technical reviewer of many prestigious journals. So without any further delay, I request Dr. Masood to please start the webinar. Over to you, Dr. Masood. Thank you.
Thank you very much.
Dr. Masood, can you please share your slides?
Okay. Yeah, is it shared?
Okay, yeah, it's shared now. You may start now. Thank you.
Okay. Thank you, Dr. Noshawan, for such a comprehensive introduction. As you all know, my name is Masood Rahman. I would say good morning to the audience who are based in UK and good afternoon to the audience in Pakistan. So the title of my today's talk is Human Exposure to RF Fields. I would just skip the introduction because Dr. Noshawan has already gone through the kind bits about me. I'm part of Center for Communication Sensing and Imaging here in Glasgow. It's a center that works on multiple themes, and some of the key areas where we are working are listed on this slide. So we work from blockchain wireless networks to intelligent reflective surfaces, antenna research, signal processing, free space optics and wireless backhaul, wireless for healthcare, self-organizing networks, network resilience, and artificial intelligence-driven designs. I'm part of the antenna research cluster. We take a holistic approach here at Glasgow. We have the facilities, world-class facilities in James Watt Nanowatt Fabrication Center. We have got the measurement chambers, anechoic chambers, the modeling tools, and all the testing equipment. So right from the conception of the antenna design to the modeling, optimization, prototyping, and testing is being done on a number of themes here in Glasgow. Some of the key areas where we are working include ultra-wideband, GPS and satellite, Bluetooth and near field antennas, millimeter wave, nanotechnology and terahertz, human exposure, implantable devices, and the wearables. So some of the examples of our fabricated antennas and tested and published work is shown to you. So that is just a brief introduction of our group here, research group. We have got around 50 academics and more than 80 postdocs and PhD researchers who are working in different areas. And we are also part of Scotland's 5G Centre, which is one of key 5G centres developing 5G testbed for experimental purposes. Right, so coming back to the topic we are discussing today, that's the brief overview of my talk today. First, I will introduce the problem. Then I will go through the human body exposure to RF fields covering numerical body modeling to attain a flexible human body that can offer different body postures, and again we can include different surrounding objects including desktops, for example chair and tables. Then we will go through the modeling of human body exposure system to evaluate the exposure of human user to the environmental radio frequency radiations. Then I will present some results based on the evaluation of exposure extent, employing specific absorption rate distribution, electric field, and temperature rise. And finally, I will summarize and give some recommendations. Why we need to do some research in this area? We are constantly surrounded by electromagnetic waves that are being emitted from a number of sources, either fixed or mobile. Some of the examples, Wi-Fi hotspots we all are using, mobile phones, laptops, the base stations, and nowadays with the emergence of 5G, IoT, wireless sensor networks, we have got electromagnetic wireless applications in a number of areas that are covering almost all fields of our daily life. So we have got the applications in medicine, we have got the application in sports, we have got applications in entertainment, infotainment. So a whole set of applications are there which are exposing the human users to a number of electromagnetic fields. Now, recently there are some events surrounding the 5G, and particularly in some Western countries, there was an uproar among the public with the rumors that 5G is giving rise to radiations that are causing coronavirus pandemic. So COVID-19 is spread due to the 5G installments, 5G base stations, although there are no 5G base stations still installed, but due to this misunderstanding, a number of events has happened where base station antennas are being damaged. This misconception among the general public needs a detailed study of human body exposure to rule out any kind of health hazards pertaining to 5G or even to the 4G and other electromagnetic sources. Also, it is important to analyze whether these sources are causing any health hazards or not. So this study is an effort towards this direction, and we have got, we all know that we have got some organizations that are monitoring, that are giving some standard guidelines to make the public safe from the electromagnetic exposure. In service and proposed communication systems have got various electromagnetic sources, and these electromagnetic sources are emitting radiations. If their strength is enough to a certain extent, they can cause severe health problems in general public. In past, cancer was quite often related or understood to be related or thought to be related to electromagnetic radiations, although there is no direct evidence available. But anyhow, IEEE, ICNIRP, and FCC are the key organizations that have provided principles to avoid health hazards caused by electromagnetic exposure. So all the portable devices, all the devices that are serving general public and occupational workers, they need to adhere to these rules, these principles. One of the key metric that is being adopted by these organizations is specific absorption rate, which is a measure to observe the level of energy absorption into the biological tissues and monitor the amount of danger. The effect of these electromagnetic exposures on the performance of human users, as I mentioned, is although investigated in detail, but further studies are needed because of the emergence of new applications and because we are moving towards new spectrums. In this study, we have chosen the environmental exposure on a number of frequencies to cover a number of electromagnetic sources and analyze specific absorption rate and the extent of hazards caused by the RF signals. Briefly, what is specific absorption rate? Although it's a very basic for most of the researchers who are working in the field of antennas and electromagnetics. Specific absorption rate is a measure of energy absorbed by living tissues. IEEE C95.3 standard provides the definition for the specific absorption rate. It is a volume average measure and provides the rate of the incremental energy being absorbed by an incremental mass contained in a volume element of a given density. We are more familiar with this definition of SAR that is widely being used in papers and in texts. So in this definition, specific absorption rate is basically related by the conductivity of the tissue in Siemens per meter, electric field, and mass density of the tissue in kilograms per meter cube. The guidelines are slightly varied among IEEE and ICNIRP. Since we are based in Europe, so we follow ICNIRP's regulations. The basic restrictions take 6 minutes exposure into an account from the frequencies starting from 100 kilohertz to 10 gigahertz. Now, occupational workers who are constantly exposed to electromagnetic fields, who are working in the environment which is constantly bombarded by the electromagnetic radiations, they are more prone to the health hazards. So the guideline says that the allowable maximum specific absorption rate is 0.4 watts per kilogram for the whole body, which is basically calculated on 10 gram tissue volume. And the allowable value is 10 watts per kilogram for the localized SAR in head or torso. For the public, the restrictions are even stringent, and the permitted level of the exposure is lower. That is 0.08 watts per kilogram for the whole body SAR and 2 watts per kilogram for the localized SAR. So that is the set of regulations that all the manufacturers have to adhere when they are developing new electromagnetic sources, for example, mobile phone antennas, for example, base station antennas, or the notebooks and laptops and other devices that basically are being used by human users and that can cause the electromagnetic radiations. Just briefly, Most of our talk is focused on human body exposure, and more focus is given to the brain exposure because of the sensitivity and the thought among the public that brain development can be affected by the electromagnetic exposure. So some of key areas that can be affected are frontal lobe or the parietal lobe, that is again regarded for the movement, and again brain stem is there, the cerebellum is there, you can see, and when we are discussing later the hotspots, you can refer to this figure to see that which area we are referring to. And temporal lobe is there, that is responsible for the language and so on. So that is the anatomy of human brain. Let's begin our quest towards the exposure of human body. So first step is to attain a usable model. So human body modeling is quite important in this direction because it provides us with flexibility of investigating a number of scenarios without going into the actual in-field testing. And electromagnetic solvers, these softwares are in the market for a number of years, and their accuracy is quite established now. So a number of human body models are available that are quite complex in nature, that are quite offer high resolution. But if we employ these models with all these surrounding objects, and if we take longer distances into an account, then the number of mesh cells are so high that sometimes computational time is unrealistic, and sometimes computational resources cannot support these kind of simulations. So as a first step, we developed a simplified model that can offer us flexibility in terms of repositioning, so we can take into account a number of body postures, for example, sitting, standing, writing positions, and reduction of numerical error due to the boundary approximation was another target, and also the faster computation due to the reduced complexity. So we have adopted the strategy to keep the human head, which is more sensitive, as a 5-layer object, as a 5-layer model, and the torso as a single layer homogeneous model. So the approximation was such that torso is represented by muscle tissues, while head has got the skin, skull, then the spinal cord and the brain, both types of the brains. So this slide is analyzing the SAR values for two models: the complex model that is offering very high resolution, and then a simplified model developed by our team. So you can see in this figure that the difference in the physique, in the shape, is very minute. So we are representing the curvatures of the body quite efficiently in both models. But this model, the high resolution model, is being represented by very fine details, very fine mesh, as compared to the low resolution model here, which in which we are using spheres, and we are using cones, and a combination of very basic structures offered by CST Microwave Studio. The values I will summarize on the next slide, but on these figures you can see that location of the hotspots are almost similar for the two models. So you can see the complex model, which is exposed to a continuous wave located at one wavelength apart from the body. Again, hotspot is on the arm, on the tip of the arm, for both models. And also for the head, you can see that distribution is almost similar, with most of the energy contained on the neck area. And if we look on the cross section of the head, then you can see that most of the energy is again concentric on the neck area and the cerebellum side. So this distribution shows that our low resolution model is efficient enough, accurate enough to provide the SAR distribution, which is equivalent to the high resolution model. Now, what benefits we get from the low resolution model? Again, this table provides a comparison between these two models. You can see that high resolution model is having a specific absorption rate in terms of a microwatt per kilogram. The values appears to be 133 for body, 71.5 microwatt per kilogram for head, 71.1 for the brain. The values for low resolution model are quite close to the values we have attained from the high resolution model. And if we compare the locations, they are also quite similar. So parietal lobe area for the brain, and neck area for the head, and the left arm or left hand for both models for the body area. Relative difference is maximum 3.7% for the body, and that is quite acceptable. If we look at the number of mesh cells, so we have reduced from 15 million mesh cells down to 3.8 million mesh cells. That brings down the simulation time to 2 days for our most complex exposure scenario, as compared to 5 days that were being used by the computer when we are using high resolution model. So based on this comparison, we are confident enough that our low resolution model is quite accurate, and we can utilize it for our exposure studies. Right. So exposure system design, we have analyzed, we have taken into account a number of exposure scenarios for the occupational workers who are the worst sufferer of the incoming radiation. So general public is less exposed to the incoming radio frequency signals as compared to the workers who are working in an environment which is constantly exposed to the radiations. For example, people who are working in an electromagnetic lab, or the soldiers who are working in the labs developing these antennas and electromagnetic sources. So this figure is giving you an idea that what type of scenario we are going to analyze. We are going to use the horn antennas as a source of the electromagnetic energy, 2 horn antennas for 2 frequencies. So the dimensions are given here. The models are 84001 and 84002 with maximum dimension of 793 millimeters. We have again considered 620 millimeters height of the antenna from the ground to level a person who is sitting on a chair. Right. So when we modeled the exposure system, so our antenna is located here, and the user is sitting at a distance depicted by value c. If we calculate the distance by using again Pythagoras theorem, the total distance a plus d appear to be 3319 millimeters. Then since our antenna is located here and the body is the user is considered to be sitting at an angle, we calculated the angle to be 77 degrees. So our continuous wave is angled at 77 degrees. How we came up to the conclusion that our body is exposed to the continuous wave instead of the antenna itself, and the person is located in the far field. So we use the far field equation, r is equal to 2d square by lambda, and by using the distances a, b, and c given here, it appeared that at frequencies of interest 1206 megahertz and 448 megahertz, again our user is far enough to be located in the far field of the antenna. So this video is showing that starting from this point, again the maximum value 2300 millimeters here. So the user is far enough from the antenna because the distance is 1877 for R at 84,001 antenna, and 84,002 antenna it is 3499. So based on these calculations, we came to the conclusion that it is safe enough to use the continuous wave as the source, and incident power density is 0.65 watts per meter square for 1 watt incident power. Again, we use standard CST Microwave Studios settings. So the area is being the incident power density is being calculated by the area, by the power 1 watt divided by the area of the exposure. Right. So since our user is located in the far field, it is not inside the near field of the antenna. The free space path loss that is caused by the distance between the antenna and the user location needs to be taken into account. So we consider 720 millimeter exposure from the body, that is quite near to allow one wavelength, while actually the body is located at 2520 millimeters away from the antenna. So free space path loss was calculated by using 4 pi d over lambda whole square and the standard equation, and it appeared that the actual value of the received power is 0.877 milliwatt. So that value is being used to obtain a normalized specific absorption rate in the next few slides. Right. So we'll begin with the exposure of the body first by taking 1206 megahertz into an account. Material properties are given here in terms of permittivity and conductivity, electric properties. In the model, we have included a table, a chair, and body is being represented by the muscle tissues, while head has got 5 layers, 5 tissues. So skin, muscle, skull, brain, and spinal cord. So at 1206 megahertz, the values being utilized in the simulation are given here for the epsilon and for the conductivity. These values are taken from standard sources, especially Camilla Gabriel's published paper that is widely being used in exposure studies and being established as a benchmark. Right. So for this exposure, we have got 2 body postures, being considered. One is the user is sitting in straight arm position, while in other position the user is sitting and typing on his laptop probably, or writing something. So that is being called as typing position. So the incoming wave CW is at the back of the body at 730 millimeters, and you can see that the exposed body is being deposited by the incoming power, the specific absorption rate. You can see here that the maximum deposition is happening at the backside, of course, and then the maximum area which was exposed is observed to be the feet of the user. So that's for the whole body, averaged over 1 gram tissue volume. While if we consider the head exposure, then the values were quite low. So for both the body postures, almost distribution is similar, and you can say that the inner organs of the brain are quite safe. So the maximum value is 150 microwatt per kilogram, but no red spots, no red colors can be observed. The noted values are being summarized in this table. In the straight arm position, the maximum SAR observed for the whole body was 142 microwatt per kilogram. That is well below the allowable value of 0.4 watts per kilogram. The location of the maxima is left hand being observed for the straight arm, while for the typing position it shifted to middle back. So you can see that left hand tip was disappeared in the typing position. It was not directly exposed to the incoming CW, so the location of the maxima was shifted to the middle back. The value was also slightly reduced. For head and brain, the values are quite similar, and locations are also quite similar. So back neck for the head exposure and parietal lobe for the brain exposure. But values are again well below the allowable exposure of 10 watts per kilogram, the localized SAR recommendation by ICN-IRP. So from this study, we have sufficiently ruled out the possible health hazards of incoming CW that is exciting the body, that is exposing the body at 1206 megahertz. So all the devices that are working in this frequency range, particularly the GPS signals that are basically exposing the body and at this frequency, so we can say that these systems are safe for human body. Now the other frequency was 448 megahertz, because most of the medical equipment is working in this frequency range. So we have also considered this frequency. Again, the body and head model are restructured to represent straight arm and typing position, and we have utilized a table and chair in the model as well. The location of the incident wave is at 730 millimeters away from the body to incorporate one wavelength, and then again the electric properties are summarized in this table. Now, if we evaluate the specific absorption rate distribution here, we can see that the maximum specific absorption rate is now again on the left hand, but you can see that location is quite similar, but left hand tips is here, while here is left arm. So slight shift is there, of course, by the restructuring of the body by changing body posture, and that is quite understandable because the movement of the body do initiate a change in the channel and change in the specific in the power distribution and the electric field distribution. If we look at the cross section of heads to observe the localized SAR in the brain, then again the distribution is evident that the inner organs of brain are quite safe. If we look at the table that is comparing both positions, both postures, then straight arm for 448 megahertz exposure results in a body maximum SAR of 79.3 microwatt per kilogram, and the location is left arm. while for the typing position the value is 102, and then the location is left hand again. The difference here is more than what we have observed for 1200 megahertz exposure, around 20 microwatt per kilogram, although it's not very significant, but again you can see that at lower frequencies any change in body posture results in slightly bigger specific absorption rate changes. For the head and brain exposure, the values are again quite similar, and locations are also quite similar, because again the head is not causing any change in the posture. So left back neck and spinal cord are the two areas which are being highly affected, I would say, not in terms of health hazards, but the hotspots are located there for the two exposure conditions. And again, from these values, it is quite clear that exposure at 448 megahertz to incoming CW located quite near to the body does not basically contribute much to the exposure, to the deposition of energy, and the deposition of energy is well below the safety guidelines. So ICNIRP's recommendations for body 0.4 watts per kilogram, it is well above the values that are being taken by the body here. So 79.3 or even 102 microwatt per kilogram is well below the permitted values. So it is safe to assume that the human user who is exposed to the incoming CW at 448 megahertz is also quite safe for the electromagnetic usage. Next frequency was 1600 megahertz. Again, this frequency was chosen because a number of microwave frequencies are being utilized for a number of components, number of applications, and again to satisfy some of our clients. The human body is again exposed to an incoming continuous wave that was resonating at 1600 megahertz. The electric properties are listed here. So in this exposure, we are basically studying the human body in standing position. Okay, so we have earlier studied the sitting position, the writing, and straight arm, but here we are considering now that human body is being exposed to the incoming CW when the user is standing. And also we have considered a number of exposing scenarios. So the incoming wave is coming from the front part of the body, or coming from the back part of the body, so back exposure, front exposure, or the side exposure. So maybe the source is located at the side of the body, so arms and legs are being exposed more as compared to the torso again. So chest and other areas, or back and other areas. So we have considered three possible scenarios. The used muscle, again we have used the same body with the single layer torso and multi-layer head, and the values for permittivity and conductivity are given here at 1600 megahertz. Right, this slide, these videos gives the exposure of the body to electric field. So you can see that incoming electric field, if the source is located at the front part of the body, so frontal exposure results in this kind of electric field distribution. So the body scattering the reflections and the refractions from the body organs is quite clear in this video. So you can observe that body shape is causing the refractions and reshaping of the electric field waves. Most of the, again, you can see here the tip of the nose is the area, the frontal part is the area of the body where electric field is hitting most, and it has got the maximum hotspot here. So most of the red part here. So other parts are yellowish, so lower value of the exposure is there. That is being confirmed by the SAR distribution. So in this figure, you can see that if we consider head, which is more prone and more sensitive to the exposure, you can see that in the front cross section here, most of the areas are quite safe. In the side cross section, it is quite evident that this area, the nose area and the neck area, is more exposed, and it is being also confirmed by the top cross section distribution. Right, so for the back exposure, we have again analyzed the electric field, and you can see here that again most of the energy is being deposited in the neck area here. Okay, so the refractions and scattering are quite clear from this video for both the body and the torso, body, torso, and the head. And most of the energy, most affected part is head and neck. But what are the values? So you can see that the maximum value we are being observing is 300 microwatt per kilogram in this legend. So the values the body is getting, the maximum value is 300 microwatt per kilogram. That is well below the allowable range. If we look at the side exposure, again, this distribution is giving an idea that which areas. Now you can see that since there are less discontinuities, and then the shape of the head is more smoother, not much energy is being deposited. So electric field deposition is quite low in these areas as compared to the discontinuities that were being observed for the nose and the neck. So if we look at the figures here, again, this side is more affected, and that is understandable because that area is directly exposed to the incoming continuous wave. But again, the values are very low in the range of 300 microwatt per kilogram. That is well below the allowable range of specific absorption rate for localized head SAR. Another interesting way to confirm is to use the temperature rise. So in the ICNIRP's guidelines, it is stated that if there is a rise in body temperature by 1 degree centigrade, then that is considered as a sufficient exposure. So that exposure is not considered as safe, right? So if we expose the human body for 6 minutes and we observe a 1 degree centigrade rise in the body temperature, then we have to reconsider the usage of that electromagnetic device. So Penny's bioheat equation is widely being used to analyze the temperature rise. The equation is being given here. We use a number of parameters in this equation, including specific heat capacity, temperature rise, material density, heat generated by metabolism, increase in blood temperature, thermal conductivity time, specific absorption rate, and blood perfusion rate. If we, in order to simplify our analysis and to relate to our numerical study, there is no blood perfusion because we are not using it. So if we avoid that, if we not consider that, then we can simplify our equation to this value. Okay, so only heat capacity, temperature rise, and time is required if we know the specific absorption rate. So since we know the specific absorption rate from our previous discussion, and heat capacity values are known at this frequency taken from the database given by ITIS Foundation website, we have calculated the temperature rise for 6 minutes exposure for the human body, especially for the head tissues for 3 exposure settings. at 1600 megahertz. So you can see in this slide that temperature rise is way below 1 degree centigrade. So the maximum temperature rise is probably 0.00968. Okay, so 0.000968 for muscle tissues inside exposure. So that is the that was a specific absorption rate. So the temperature rise, the maximum value of temperature rise is in the range of 0.000141. Again, this value is way below the permitted or the value that is taken as a hazard, 1 degree centigrade. So that's another way to confirm the safety of the devices that are available. Right. So in the final setting of exposure study, we have considered an exposure of the human body, which at lower frequencies. Again, these frequencies are used for some of the devices that are operating for medical purposes. We have used the monopole antennas, and we have now included a desktop, a keyboard, chair, and the desk for this exposure. That is the antenna structure and the dimensions for two frequencies. So we have considered 75 megahertz and 29 megahertz frequencies. The distance, the maximum distance R, is now 790 far field distance and 1348 millimeters. But our body is located nearer to the antenna, so now we cannot consider the CW exposure. So the antenna structures were itself being used in the simulation studies. So these simulations take quite long because of the larger area in the computational region. So human body is located in the near field of the antenna now. The electric properties for 75 megahertz exposure is being summarized here. Again, head is considered as a multi-layer object, while body is being represented by muscle tissue homogeneously. For the exposure, again, we have considered two positions, two body postures, straight arm and typing. And we can see here in this slide that the values being the specific absorption rate values being given by the exposure is in the range. Maximum value is 2500 microwatt per kilogram for the body, and in the maximum area that is being exposed is the feet because of the reflections from the ground plane. The other thing is, in this structure, we are using 2 gram average instead of 1 gram average tissue because of the limitation of the computational sources. Because if we take 1 gram averaged volume into an account, then we have to represent the model with very fine mesh, and that it is not possible for the computational resources we have available for these simulations. So instead, we have used 2 gram averaged and then normalized it to represent to basically see their adherence to the given standard values. This table summarizes the values we have obtained for 75 megahertz direct exposure to the antenna where the user is located into the near field of the antenna. So if someone says that a device that is operating very near to the body, very high exposure, then how safe it is. So we can see that for the straight arm body posture, the maximum amount of SAR was 79.3 for whole body exposure, with left arm getting the most of the exposure, most of the absorption. For the typing position, the value is 102, and left hand is the area which is most affected. If we move to the 29 megahertz, and that is our final setting for these exposure studies. So electric properties are being summarized here. and we can see the results here. So you can see again that the exposure now is quite high, 8,000 microwatt per kilogram, because of the size of the antenna, of course. But again, the inner organs of the head are quite safer. 800 microwatt per kilogram is the maximum value on our legend. For two body postures, again, if we look at the table, the values now the maximum is 7,420 microwatts per kilogram because of the size of the antenna. So you can see that even if the body is getting this amount of specific absorption rate, that is way below the permitted value of 400,000 microwatt per kilogram. So from this discussion, if I summarize, and we are near to the allocated time. From this whole discussion, from the results of specific absorption rate, from the results of temperature rise, from the electric field distribution, where we have exposed the body to CW with the power density of 0.65 watts per meter cube, Weber per meter cube, sorry, and the antenna itself at frequencies of 29 megahertz, 75 megahertz, 400 megahertz, to 1206 and 1600 megahertz frequencies, we haven't noted any serious harm, okay, in terms of health hazards. So all these frequencies, the devices that are operating at these frequencies, the energy deposition into the body is well below the permitted value of 0.4 watts per kilogram for the whole body, and 10 watts per kilogram for the localized SAR. So head maxima locations for SAR changes depending on the incident, side, frontal incident or back incident or side incident of the specific of the continuous wave. We have also observed the distortion of electric field due to the scattering, refraction, and reflection from the head and from the body. Penetration is minimal. No internal organ of the head or the brain are being affected, and since the temperature rise is quite low, it is very safe to assume that there are no serious health issues related to the electromagnetic exposure. So the devices that are operating at these frequencies, and it's a continuing study where we are going to study more exposure to include more devices and more frequencies of 5G to ensure public that these devices are safer to operate. So thank you very much for your attention, and if you have any questions, I would be happy to answer. Thank you, Dr. Noshirwan.
Thank you, Dr. Masood, for an interesting talk. So we have some questions lined up. I asked you one by one. So the first question is it true that cell phone usage, whether less or more, does has irreparable damage to some extent to the human brain? And what is the safe timings, minute-wise, that one can use a cell phone? Also, even though it is still in development stages, does 5G have more negative effect on human brain than a 4G?
I hope that with these conclusion, things are more clear. Although there are rumors and there are misconceptions related to 5G, related to 4G, related to continuous usage of mobile devices, or exposure to base stations is there. But these studies, these simulations, these numerical studies confirm that for the standardized exposure of 6 minutes, these devices are quite safe to operate. Now, these studies are, I would say, not conclusive in the term that we don't have exposure for hours. So sometimes people are talking on the phone for maybe hours, and they do, observe, they do feel some temperature rise or some hotness on their ears area. that could be related to the temperature rise, but again, whether that temperature rise is enough to cause any harm, this question is still needs to be explored. But from this study, you can see that the exposure that is being standardized by the ICN, IRP, and FCC and IEEE that permits 6 minutes exposure for occupational workers who are continuously exposed to the electromagnetic fields. Operation is quite safe. And the guidelines also have got a 30 minutes exposure for the occupational workers, and there are some studies that have confirmed that even the 30 minutes exposure is quite safer and there is no serious health harm attached to these exposures. Again, you know, it's a phenomena that needs to be investigated more because of course it is related to our health. So studies are going on, we are also investigating it, but these simulations do confirm that there is no matter of serious concern attached to 5G, and probably it's just a misunderstanding. Yeah. So any more questions, Dr. Noshirwan?
Yes, the next question is, what is the SAR for 5G?
Well, the values, the standard values for SAR remains the same for 5G. Okay, so you can see that the range of frequencies that are being considered by the standard bodies are from 10 kilohertz up to 10 gigahertz. Right, so most of the lower end 5G frequencies are being covered. What about the millimeter wave frequencies? Still studies are going on. These frequencies are not well standardized at this point. So the standardization studies are going on. There are no conclusive studies out there that can give you some specific values. So 5G exposure, not 5G, but millimeter wave exposure is still in discussion. But as you know, that penetration depth is quite low at 5G. So we all know that due to the wavelength, the penetration is quite low. So most of the energy deposition is restricted to the skin area or maybe to the muscle tissues. So again, it is quite evident that the inner organs, especially for the inner organs of the brain, these are safer even at millimeter wave frequencies. So again, studies are going on, but these are the fundamental things that do exist in millimeter wave frequencies as well. But the lower end 5G frequencies, they are quite safe to be used, as evident from these studies.
Thank you. The next question is, the study shows analysis in a controlled environment. So the questions are, first 70-degree angle was chosen. How would it vary between 0 and 90 degrees?
Well, the 77 degrees angle was chosen in one of the studies, right? In the other study, the angle was 0. It was the incoming wave was parallel to the body, so there was no angular difference. So you can note down that in both these studies, the exposure limits were well below the standard values.
Okay, I think the other part of the question is, in real scenario, exposure is from low megahertz to millimeter wave nowadays. So do the simulations tools have the capability to do the analysis at multiple frequency in a random electromagnetic environment?
Well, the simulation tools do not have got capability to analyze random frequencies in this wide range of spectrum. We can simulate on certain frequencies, or we can simulate on a narrow band, but again, they have got their limitations because you need probably a supercomputer with huge size of mesh if you want to incorporate all these frequencies starting from a few megahertz up to 60-70 gigahertz. So that is not possible in a single go, but of course they can simulate these exposure studies on single frequencies or even smaller bands, so that's possible.
Okay, the next question is the SAR is purely based on power absorption by human tissues, whereas isn't it the resonance caused in human tissues or cell is independent of power? So can resonance in human cells or tissue can be created with a very low power signal as well?
Well, I do agree that resonances can be caused by low energy as well. Interestingly, I haven't presented another study where we have developed an exposure system for dosimetry studies. So we have taken the human brain cells in a small cavity resonator and exposed it to 125 kilovolts of incoming electric field. So these studies also show that the deposition of energy into the cells itself is not causing. I would not say not causing, but I would say that they are well below the standard values. So whatever the standard is being adopted by ICNIRP or IEEE, the deposition or the exposure or the resonances or the degradation caused, it is well below the standard values. These studies, when we look at the electric field, then of course we can see how the body is responding to resonances. Specific absorption rate is true that it is only giving the absorbed power, but electric field analysis is there where you can look how body is responding and what is causing resonances, what area are causing these resonances, these changes in the wave parameters.
Okay, there's a long list of questions, so I think there's only time for one question, so I select the one that is in front of me, and then if other participants have any question, they can ask the speaker by writing him an email. So the question is, can the speaker share a scenario where the exposure has gone beyond the allowed limits and also the temperature rise of more than 1 degree?
Well, we haven't observed any abnormal exposure or temperature rise in these studies. So we have studied 5 frequencies up to this point. The millimeter wave frequencies, they do have got more specific absorption rate and higher temperature rise for the skin areas. But again, I have mentioned that penetration depth is quite low, and the inner organs are safer. Studies are non-conclusive for millimeter wave frequencies, the exposure studies. So we are trying to simulate the scenarios. We are using power density as well as another measure to observe the exposure in continuation and in parallel to specific absorption rate. These frequencies, for example, 60 gigahertz or for example 28 or 38 gigahertz, the exposure at these frequencies is still undergoing. Okay, the investigation is still undergoing, but again, due to the low penetration depth and the low wavelength, again we say that these frequencies are safer to be used, but non-conclusive yet.
Okay, thank you very much. I request all the participants, if you have any further questions, you can write an email to the speaker directly for your questions, because due to limitation of time, I am unable to include all the questions. So I would like to thank Dr. Masood for your very interesting talk and for your time that you spared for our chapter and for our community. I hope to see you at future platforms as well. Thank you very much.
Thank you for having me. It was a pleasure to give a talk to such a vibrant audience, although I cannot see, but from the questions it appears that people were very interested. Thank you very much.
Thank you, Dr. Masood. Hope to see you at some later occasion as well. Till then, bye-bye.
Thank you, Dr. Noshirwan. Thank you.
Bye.
Bye-bye.